get started. So before we actually start tonight, I would like to show my respects and acknowledge the Bedegar people who are the traditional custodians of the land, of elders past and present, on which this meeting takes place. So welcome, my name is Hengst. I'm the outreach manager here in the School of Physics at UNSW. You can see my face around the campus. Just an announcement, we will be having a telescope session after the presentation, but it may take a while for something set, but Duncan's talk goes for about 50 minutes or so in Q&A, so hopefully that's delayed enough to head out to the physics lawn where Matthew Freeman will be setting up a telescope. So stick around for that, because I believe Mars and Venus is actually up, so there'll be lots of objects to look at. Alright, so finally over to the main attraction, I guess. So it gives me a great pleasure to introduce tonight's speaker, Dr. Duncan Wright. He's earned his PhD from the University of Canterbury, New Zealand, and has worked with the Royal Observatory of Belgium. He's currently working here in the School of Physics with a joint position at the Australian Astronomical Observatory, also known as the AAO, which is one of Australia's leading research facilities in astronomy. Duncan's primary research interest is in planetary sciences, and one of his most notable achievements is that he led a team here that discovered a planet in the habitable zone in a nearby star some 14 light years away. And at the time, it was actually the closest potentially habitable planet, but that got superseded by a discovery in the last few months, unfortunately. So, but that was, there was an exoplanet discovered around our closest star, Proxima Centauri, to our solar system. But no doubt we will be speaking about that, and I'm really looking forward to it. So I give you Dr. Duncan Wright.
Thank you, and thank you for coming. Just to let you know, I've turned the air conditioning on because it feels a little hot to me, but if it does get cold, let me know, because there are certain locations that get blown on by the air conditioning. Okay, so this evening my talk is entitled Hunting for Life Around Wobbly Stars. What I'm talking about when I have that title is the method that I particularly use to discover exoplanets around nearby stars, that is the Doppler method. So I'll be describing that. But I also wanted to put things a little bit in perspective with regard to the discovery of life outside our solar system in the galaxy. So I've got a little bit of the talk on some thoughts with regard to the Drake equation and some other sort of interpretations with regard to that in terms of trying to find life in the galaxy, not necessarily via the detection of extraterrestrial signals, but rather through the discovery of life by looking at the host exoplanets of that life. So I have a little bit about that. So I will start out with relating how exoplanetary science is involved in the search for life. We'll also discuss a little bit about the bottlenecks in terms of how life can develop in the galaxy, how we are addressing this in astronomy, most specifically exoplanet astronomy, and then what can we can achieve now, and this relates most directly to my research in terms of exoplanet discovery, but also what is in the future and how that will address trying to find life in our galaxy and what the probabilities of that are. Okay, let's see how we go. So, one of the things that exoplanetary science is involved in terms of the search for life is defining where we search for life, and also, based on the limitations of the science, where we should actually look for life, where we could possibly find life. One of the simplest definitions we use in terms of a habitable planet, you've already heard that mentioned earlier with regard to a couple of discoveries, is we're talking about water-based life. We're talking about life where we believe that water is the major solvent involved in all the chemical reactions that go on in life. So we define a habitable zone in its simplest terms as a planet which has a solid surface, so a rocky planet, where the temperature of that surface is suitable for the presence of liquid water, so that life, were it to exist, could have liquid water as a solvent. So we're talking about a very simple version of the habitable zone. I wanted to get that out there because you're going to see a lot of potentially habitable sort of thrown around, and that's what we're talking about, a simplified habitable zone where a planet, a rocky planet, could have liquid water on its surface. So how does exoplanetary science, how is that involved in the search for life? I sort of came up with 3 areas in which we're trying to progress in exoplanetary science that involves the search for life. That is, we're trying to find potentially habitable planets. This is something we can do. The little stars down the side here are trying to give you an idea of where we are in terms of what we can do, what we can't do. Green, we can do this, but it is worth noting we can only do this for a very limited sample of stars, and a very limited sample of what we believe could be potentially habitable exoplanets. That sample is limited basically to the small stars, not sun-like stars, but the small stars, and I'll come back to that. Where a potentially habitable planet is basically defined just by these 4 things. In a simple sense, we know information about the host star, we know about the size of the exoplanet in terms of its radius, its mass, and its orbit, sort of the period of its orbit. So a few simple parameters. We can define whether we think it could be potentially habitable. Now there's a lot more that actually goes into whether something is habitable. Based on those 4 parameters, Venus would be habitable, but it's not. So there is a lot more to it, but that's the simple sort of definition that we go for at the moment, and those are the parameters that we can measure. But one of the next things that we want to be able to do, and that we're developing instrumentation to be able to do, and something we're even trying to do now with the instrumentation we have, most specifically the Hubble Space Telescope, is trying to examine the atmosphere of exoplanets. And that is a real challenge. But the idea there is to try and understand the chemical makeup of that atmosphere. That tells us a lot more about the actual temperature of the atmosphere as opposed to the temperature as assumed from these simple parameters. Whether the atmosphere is in equilibrium or disequilibrium, things about the rotation rate of the planet, all of these things play into how habitable that planet could actually be. And maybe we still don't really know much about this because it's at the very boundaries of what we're able to achieve. It should be plausible to find the signatures of life in a detailed study of the atmospheric makeup of an exoplanet. This is something that we believe the instruments that are coming online just in the next few years will be able to achieve. Most specifically JWST, the James Webb Space Telescope, and I'll talk about that a bit towards the end. And then what we would also like to do, but at the moment there is no instrumentation that's being planned that would actually be able to achieve this, because it is a particularly challenging task, is know something about the surface environment. That is actually knowing sort of the quantities, relative quantities of land mass to water and things like that. Some of that can try to be derived from the atmospheric composition, but knowing information about the surface environment can also tell us a lot about the likelihood that the state that we observe the planet currently in is going to be the state that it's going to stay in for a long time or not, things like that. The possible presence of tectonic activity can help us understand whether the signs that we thought were life, maybe, or didn't think were life in the planet are actually due to volcanic activity or whether they're not, things like that. They can tell us a lot about the chemical makeup and things that we've seen there as well. Unfortunately, that's not planned instrumentation able to achieve that at the moment. This is a particularly challenging task. So we're going to be focusing on this. This is the area that I work in most particularly. This is the area that's going to be coming online and available to us as astronomers in the next few years. Just give you one moment. Just before we go into too much more detail, because we will be coming back to this, I just wanted to go over a review of the thinking on the likelihood of the development of life and intelligent life. So this is the Drake equation and a slightly different reimagining of that, and how we can try and address the parameters involved in something like the Drake equation. So I imagine quite a few of you are familiar with the Drake equation. In order not to make too many mistakes, I'll go over to my notes. But the Drake equation was invented by Dr. Frank Drake in 1961. It was not designed to be a rigorous sort of an equation, but rather to inspire discussion for the first SETI meeting, the Search for Extraterrestrial Intelligence. And the idea here is basically you're trying to estimate the number of detectable civilizations through transmissions. So things like the radio waves that we send out into space, those would be detectable transmissions. And the parameters involved here give us a good sort of an idea of what to think about. And I'm going to rewrite these a little bit in terms of the things that I consider and in terms of what we already know in the next slide. So things involved are things like where N here is the number of detectable civilizations. You've got the average rate of star formation in our galaxy. These are sort of paraphrased, simplified descriptions of these parameters. The fraction of the formed stars that actually have planets, the average number of those planets that are habitable in the star, around the stars, the fraction of those planets that are habitable that actually develop life, those fraction of those planets that develop life that actually develop intelligent and civilized life, and then those civilized lives that actually develop and transmit detectable transmissions, and then the length of time over which they actually release those detectable signals. So I'm going to try and rewrite that in a slightly different way and have a sort of graphic in the background that I think is helpful, at least in the way that I think of it. So what we know now, and I'll come back to how we know this a little bit later, is we know that there is a huge number of potentially habitable planets in our galaxy alone. The Kepler spacecraft and its 4-year mission to try and tell us about the number of exoplanets was extremely successful. And it gave us information about the number of potentially habitable planets as well as just the number and different variety of planets. And what it, roughly speaking, told us was that of the 300 billion or so stars we have in our galaxy, we have something like between 1 and 6 planets for every one of those stars on average. That's an average. Some of those stars have none. Depends very much on the environment they're in. Some of them, like our own sun, have many more than that. But there are a huge number of stars, and a large number of those stars are going to have potentially habitable planets around them. That is rocky and in what we describe as the habitable zone, based on those simple things I outlined earlier. So that's the top line here, and that's not necessarily a solved problem, particularly when we get down to those lower mass, Earth mass planets. The numbers are actually a little bit more sketchy, because as I'll show with real data from Kepler in a little while, discovering Earth mass or Earth radii and smaller planets is extremely difficult, even with the incredible Kepler telescope. But it did tell us, based on what we could get, that there were a large number of potentially habitable planets. So that top line there, we believe that this is a large number. Now the little background graphic, the yellow, is supposed to represent sort of, here we have the number of potentially habitable planets, and then in each line we've got a different probability. This P bracket is just a style of trying to say the probability of whatever is inside the bracket. And so for these probabilities, we get smaller and smaller yellow size of the yellow bar that represents the sort of number of planets that actually satisfy all the criteria above. And I'll try and use that after I've gone through these to sort of show you the different kind of galaxies that we could easily be living in, and maybe discuss how we can narrow those down in a moment. So we've got a particular size of yellow bar, and then as we go down, the probability of forming life is obviously the first step. Once we know we've got so many potentially habitable planets, what is the actual probability of those planets forming life? And we know so little about this question, this probability, despite the fact we live on the only planet we know about that has life on it. It's an extremely challenging problem. That it comes down to a simple fact that we can't recreate life in a lab. We have some ideas. There's some interesting research I was reading just recently about the concept of life developing in sort of muddy pools where the pools were on land, they dry out, and then they get wet again and they dry out, and this repeated process creates a sort of a gelatin which is able to create the first sort of cell membranes as long as you have the appropriate materials in this sort of muddy pool. Things like that, whereas prior to that, the concept was that life was developed in the ocean. So there's a lot of work going on there, but there's still so much we don't know. We simply can't create life from nothing in a lab. And so we don't know about what the real conditions were, what the conditions are required to be able to form life. So this is very much an unknown. The next step is something that this sort of design I've got here is borrowed a little bit from Charlie Lineweaver's associate professor at ANU. He gave a talk a couple of years ago about the Gaian bottleneck, and it particularly focused on this, which hasn't really been studied a lot, mentioned a lot until he came out with it a few years ago, which is about the ability for life to transform its environment. When, and we see this on Earth. A few billion years ago, we had the occurrence of multicellular cyanobacteria, and they were able to use photosynthesis to create oxygen. It was not an oxygen environment here. We call it the Great Oxygenation Event, and eventually that oxygen environment actually ended up killing off most anaerobic bacteria that existed at the time, but that created an environment for the development of aerobic bacteria that use oxygen and live in oxygen, and so you're able to establish an equilibrium. That enabled life to set up an equilibrium that was resilient to small changes in the atmosphere. That's not necessarily always going to be the case. We don't know about the ability for life to be able to develop its own stable environment, reach its own equilibrium. We have reasons to believe, given Earth, that it's quite likely, but we don't know about that necessarily. And then there are some other steps of which we can make guesses, but it's still only guesses. That is that we have every reason to expect that once life has developed a stable environment, that it will get more complex, developing complex life, large multicellular beings. The likelihood of this next step, that like those large multicellular beings becoming intelligent, is certainly debatable. We had a long period here on Earth where that didn't happen. So there's every reason to believe that there could be many worlds out there in which life has developed, but it is not developing intelligence. And then the step where intelligent life actually has to survive long enough and develop detectable transmissions. And I've added on there or travel, and that's because of something that I'll talk about in a little bit as well. So the question I ask myself when I see these things is, what kind of universe are we living in? We don't know a lot of these probabilities, and particularly the first one, which plays such a big role. But if we imagine a situation where we have many potentially habitable planets, we consider that relatively known now, though I'll talk more about it later, then based on the probability of forming life, we could, if that's very small, if the likelihood of life formation is very small, and there's every reason to believe that that could be the case, it could be in a very special set of circumstances on Earth that form life, then we have a very small, moving forward block of planets that actually are able to form life, develop stable environment, develop complex life, and then develop intelligent life. And then for that intelligent life to develop interstellar detectable transmissions. So therefore, we could be living in a universe where there's lots and lots of planets out there that could potentially be habitable to us, or be created to be habitable, but currently aren't. Or we could be in a situation where life forms a lot, but actually that life gets snuffed out very early. This was the proposal of Professor Charlie Lineweaver a few years ago, that we haven't considered that possibility, that the probability of life actually being able to form a stable environment is quite slim. So we need to consider that as well. And then we have other options, situations where complex life develops but intelligent life doesn't. And then this is what I would probably call something like a garden planet situation, where there are loads and loads of garden worlds out there with life teeming on them, but the probability of developing intelligent life is extremely slim. And then you've got your sort of sci-fi galaxy, and there's every possibility we could still be living in that, though it's getting slimmer. That is where we're like a Star Trek universe. There are many, many intelligent species all out there. But were that to be the case, then there's a sort of argument that we should start to see that. You can do some really basic numbers, and these were very basic numbers that I just worked up. The Milky Way galaxy is not an especially large galaxy, but it's quite a large galaxy. Its size is 30 kiloparsecs. Oh, before I go on to that, I did want to say that, so obviously when you have intelligent life, there's a pretty good reason to question what is the lifetime of that intelligent life? What is the probability that it will actually is destroyed when it's still very destroyable on a single planet, or that it destroys itself? That certainly plays a role, and I haven't really talked about that lifetime issue, but it's another thing to consider. But if we consider a situation where you have a Star Wars-like galaxy, loads and loads of different intelligent species being developed, then you would expect that some of them would be able to survive for a reasonable length of time. Now, if the size of the galaxy is about 30 kiloparsecs, there it is in kilometres, and if you imagine that you could travel at about 10% of the speed of light, then it would take about 1 billion years to cross across the entire galaxy. Now, 10% of the speed of light isn't that fast. Realistically, accelerating things to 10% of the speed of light is not that far beyond our technology. It doesn't involve any special physics we don't know about, so there's nothing super about us making those assumptions. But if it only takes 1 billion years to cross the galaxy, the age of the universe is 13.8 billion years, the age of the galaxy 13.2 billion years, the age of the Earth only about 4.3 billion years. These are only approximate numbers. Then there's every reason to expect that some sort of intelligent life, if we're living in a universe where the probability of creation of life and it becoming complex and it developing intelligence is quite high, there's every reason to expect that there should be intelligent civilizations that are more than 1 billion years old. Maybe 2 or 3, maybe 4 or 5 billion years old. But if that was the case, given the complexity of travelling around the galaxy, which is not that complex, if it was able to survive for a long period of time, you would expect to see significant numbers of planets or significant chunks of the galaxy be inhabited by intelligent life. Now, keep in mind, this is not the whole sort of thing about the talk. I just wanted to give some background, some thinking. But were that the case, I would say that we should start to see over the next sort of 50 years, very much as we ramp up our astronomical exploratory abilities around our star and also further out into the galaxy, more and more that likelihood becomes less likely. The likelihood of an extremely abundant, complex, intelligent life galaxy becomes less likely as we search, because we should start to see signs of that, and at the moment we haven't. Anyway, moving back to how astronomy is addressing those things, that's really a thought process I go through. It's something I wanted to get out there, but I want to talk about how astronomy can feed into this in terms of numbers. So the first top line I mentioned is a sort of solved problem, but it's actually not. We only know numbers for particular types of stars, particular types of planets. And some of the worst statistically known numbers are for exactly the planets we're interested in. Earth-like planets around Sun-like stars. They are extremely difficult to know anything about. We do know quite a bit about Earth-sized planets in habitable zone orbits around small stars, because that makes things a bit easier. I'll talk about that in a bit. But this top line here feeds into the top line of the previous slide, which I think I can get there, previous couple of slides, the top line there. But also being able to examine the atmosphere and taking that next step and being able to maybe even see the signs of life, although that's going to be particularly challenging, is really about answering some of those next few questions. And maybe being able to tell us a bit more and clamp down a little bit more on those probabilities of what is life in the future. This part, as I said, is a little bit beyond us at this point. So just before we go to the next section, I just wanted to give a little bit of a summary. So we know there are many planets from Kepler. I'm going to talk about that a bit more in a second. About 1 to 6 planets per star on average. We know there are many potentially habitable planets. What we need is to be able to find planets on which we can search for signs for life. So we need stars that are quite bright nearby, and we need planets that are suitable, and I'll talk about what suitable is, for a search for signs of life. And part of that involves defining what is habitable, being able to study the atmosphere of the planet, and define what life could look like in the data that we're going to get. And that is a particularly challenging task as well. So what we can achieve now we're going to get into the sort of data section where I talk about what I do and what we're able to do and why we're able to do this only for a small section of the sort of stellar community, the community of all the different types of stars that we can look at. So I'll talk about exoplanet discovery. I'll have a very quick review of the techniques because I'm uncertain as to how much you know about the different techniques we use to discover planets. I'll talk about the Kepler discoveries because they've played such a vital role in our understanding of what is the sort of planetary zoo that we see out there in the galaxy, and talk about the Doppler velocity detections of potentially habitable exoplanets. The long and detailed one is the section of my particular work. and about how they are all orbiting M-dwarf stars at the moment, but about how that can still lead us to answers for the questions that we had about life developing in the galaxy, even though it's only a small section of the total number of potentially habitable planets in the galaxy. So there are a few videos I'll just run through, and I'll sort of talk over them to hopefully make them clearer than they already are, over the different techniques we use to discover exoplanets. These are videos from exoplanets.nasa.gov. So the transiting method, this is the method that Kepler used to find thousands of exoplanets. Just in the last 10 years, it was launched in 2009. Essentially, if we're looking at a time series of brightness of the star, then if the orbit of the planet is aligned just along our line of sight, then as we look at the star, we can't see the planets, remember. The planets block some of the light from the star. This is just the brightness. And as they block the light from the star appears dimmer, because all we can see of the star, we can't resolve its surface into a disk. We just see a point of light. But when some of that light is blocked, we see the light getting faint, the star getting fainter, and then as the planet moves out of the road, then the star gets brighter again. That's the theory behind it. I'll show you the reality of the data in a couple of minutes. So that's how we discover transiting exoplanets, and Kepler found thousands of those within its first, thousands of candidates within its first year of staring at just a very small section of space. Then there's the Doppler velocity method. This is the method that I use to find exoplanets. So essentially, when a planet is orbiting another star, the planet and star are actually orbiting around their centre of mass. So the star moves as well. And although we can't detect any light from the planet, what we can detect is light from the star. And when the star moves away from us, if you imagine just one particular wavelength of light that's coming from the star, when the star is moving away from us, that light is getting stretched. And when the star is moving towards us, the light is getting compressed. When it gets stretched, it's moving redward. It becomes more red, a particular wavelength. When it comes towards us and is compressed, it becomes blue. It becomes what we describe as blue shifted. It becomes a more blue wavelength. This is exactly analogous to what you experience when you hear a truck coming towards you and going past you. It's the Doppler effect. When a truck is coming towards you, it sounds higher pitch than when it's going away from you. Essentially, that higher pitch, that higher frequency, is a shorter wavelength, exactly like we see a shorter wavelength, a blue shift, when the star is coming towards us. And when the truck is moving away from you, that wavelength of sound is stretched, so it sounds like a lower pitch, a lower frequency, but actually what's happening there is it's a longer wavelength. Exactly the same as what we're using here to discover the speed of the star towards and away from us. And when we're discovering an exoplanet, we see a periodic variability of the star moving towards and away from us as the planet orbits. And in that case, the planet doesn't have to be exactly aligned so that it's blocking out the light. So a transiting planet can be detected by the velocity method, but a Doppler velocity planet won't necessarily transit in front of the star. Okay, and then there are a couple of other methods I'll run over briefly. The direct imaging method is essentially when we look at a star, there is a planet there giving off some light, but many, many times less, typically millions to even billions of times less light coming from the planet. When we cover up the star, we can reveal the planet. So essentially we use what's called a coronagraph. It's called that because to look at the sun's corona, we put a little black cover in front of the sun, and then you can see the corona, that is the outer part of the sun. We do the same sort of thing to try and find planets around stars. We cover up the light from the star using a little block, and then we can try and look for planets very close in to the star. But being able to resolve close-in planets is very, very difficult. So this works best for planets that are self-luminous, that are quite hot, quite young, and quite large, giving off their own light rather than just a small amount of reflected light. How are we going for time? That doesn't tell me much because that's not the real time. Sorry. 7, is it? Okay, that's good. That's good. We're going all right. And then we have the astrometric method. This is something that's definitely going to come to play in the next few years. Gaia is a new satellite that has just gone up the last few years, and it is getting extremely precise, incredibly precise positions for a billion stars or more. And over time, we will be able to see how the positions of those stars change relative to each other. And if you have an orbiting exoplanet, then just like with the Doppler method, but now in a different dimension, you have the motion of the star due to that orbit. And that motion of the star will be relative to other stable stars, stable in their position, and you'll be able to see an orbiting motion of the star due to that, that orbit around the centre of mass of the Earth's planet system. So I expect that in the next few years we will start to discover some planets due to the astrometric method. But at the moment that's been very challenging from the ground. It hasn't really been possible to be able to get precision enough to be able to discover those. So those are the techniques, and in summary we sort of have transits. They give us the ratio of radii of the exoplanet to the star. They're extremely good for finding high radius ratios or short orbital periods, because the short orbital period is much more likely to align exactly so that we can actually see the dip in light. Doppler velocity is good for high mass ratios. Remember, it's the mass ratio that actually changes the amount of motion of the host star as the planet orbits, or short orbital periods. Essentially, both of those things increase the gravitational pull between the planet and the host star, and the larger the force between those two, the larger the motion of the host star. And I'll talk about some real numbers with regard to that in a minute. Direct imaging is better for high mass, young, self-emitting, that means hot planets. Typically things like Jupiter sort of mass, but still around very young stars. And the astrometric method is again sensitive to short orbital periods and high mass ratios. Kind of like the Doppler method, but on a different plane. So very briefly, a couple of discoveries. The first discoveries, an example of the kind of data we got, we found it wasn't me, but one of the first discoveries of a planet around another star, 51 Peg B, in 1995, high precision radial velocity at the time was sort of 4 or 5 metres a second. That was very high precision, and we were able to find this quite clear variability. But what was confusing is it corresponds with, given that we know a lot about the host star, it corresponds with a mass of the planet of about half a Jupiter mass in an orbit that's only 4 days long. And that was really confusing. This is the prototype hot Jupiter. We didn't think that large mass planets formed close into stars. There are plenty of reasons for that. Primarily, we expect large planets to form outside what we call the ice line. Just like we see in our own solar system, the large planets are further out, the small planets are closer in, terrestrial planets. So this told us a bit about things like migration, that planets can move around if our theory on planetary formation is correct. And also we found the first transiting planets, 1999, using the STEER telescope at Tenerife, HD 209458b, one of those great HD names. This is a classic example of a transiting exoplanet. This is just because they seem to have a noisy post-transit period. I think it's only taken over a few nights. But this, you can see, corresponds to a drop in intensity, where 1 is the standard intensity of the star, of about 1.5% or so. Typically, a Jupiter mass planet will have a drop in intensity of about 1%. So this was actually a few Jupiter masses. And the ratio of the radii there means that the radius of the planet is about 1.5% of the radius of the star. Okay, so those are the first sort of discoveries. Doppler velocity exoplanet discoveries continued for the next 10 years. We found hundreds of Doppler velocity planets, most of them large mass planets, sort of greater than the mass of Neptune. I'd say it was about 300, 350 exoplanets were discovered until 2010, when Kepler launched. So we had 300, maybe 500 planets, so quite a few. Most of our planets that we knew were Doppler velocity planets found via the Doppler velocity surveys. They were observing hundreds of stars, primarily sort of sun-like stars, looking for the Doppler wobble effect. And so what we saw there was mostly Jupiter mass, Neptune mass planets. But there were some exceptions. With the development of high precision, that is better than 3 meters a second, in some cases better than 1 meter a second precision. I'll talk about that in a moment. We were able to discover planets around some M-dwarf stars that were actually getting on for Earth mass size. These were sort of 4 or 5 Earth mass planets. Now what we're talking about here when I talk about 5 meters a second, 3 meters a second, that's like if I walk a little bit faster, this is about 1 meter per second. That's the speed that we are able to measure the bulk velocity of the star moving towards or away from us. I find that incredible. We can measure the velocity of the star towards or away from us. Not the one particular part of the star, but the bulk velocity of that star, bulk motion, down to walking speed of a person. And that's what we need to find these small, low-mass exoplanets. These GL581 planets and GL667c, the GL actually means it's in a Gliese catalogue, which actually means that they're M-dwarfs, essentially very red objects. We're finding planets there with amplitudes of just a few meters per second. Amplitude 2.5 meters per second here, on this graph here. 10 meters a second for the bigger one, 2.5 for a smaller one. These ones were the GL581 planets, I think. So what we're looking at is radial velocities. You've taken lots over a long, long time period, and then you've phased them up. You've folded them on a particular period so that you can see how well the shape of the velocities fits the period. So while that went on, then Kepler launched in 2009, and it found a lot of exoplanets, about 2,000 candidates in its first year. It's come away with about 2,700. This is a nice little graphic that shows the sort of planets you find. There's actually a couple of newer versions of this, but I thought this one did a pretty good job. This is after only 1.5 years or so of data, maybe 5 quarters of data, showing that the size of the planet and the colour of the planet actually indicates its actual size, and its colour indicates its temperature. These are all relative to, actually I can't tell you, it's all relative to an Earth, where an Earth scale is about sort of this size, maybe a bit bigger even, because Kepler is really good at finding planets that are very, very close in. So all of these systems that you see here, almost all of them are very, very compact systems with periods of only 10, 20, 30, 40 days. It found very few planets that have periods longer than that, and that's just because of the geometric likelihood of long period planets aligning so that they actually cross in front of the star. It's extremely low probability of that. But what this told us is even at very short periods, there are so many planets out there to find. And it also told us about some really, really complex systems. In fact, that one's not Earth. Maybe it is Earth. This is supposed to, one of them on there is supposed to be the scale by which everything is set, and maybe it is that one. But anyway, what we found there was that there are a huge number of planets, but Kepler, of course, has its own sensitivity. It's far more sensitive to large planets because it's using that transiting method. And the bigger the planet is when it crosses across the face, the more light it blocks out, the easier it is to detect. And also it's far more sensitive to close-in planets. So it's not really likely to find an Earth-mass planet around a sun-like star. That's not very probable. It found some planets that were smaller than Earth, and it found some planets that were at the same distance as Earth, and it found some that were actually just a very few single-digit numbers that were quite similar to Earth. But that's not very high probability, but it told us so much about the kinds of planets that are out there. We came away with the knowledge that planets are everywhere. There are a huge number of planets around every star. And also, just because it feeds into the kind of work that I've done and that I want to talk about, that is that small stars, M-dwarfs, are particularly good candidates for trying to find potentially habitable planets. But there are some difficulties that come along with that I'll talk about in a bit. That is that they have more planets, and those planets are more likely to be rocky, and because of the characteristics of M-dwarfs and their habitable zones, which I'll talk about in a bit, they're actually more likely to be potentially habitable rocky planets. So they're particularly good. Now, M-dwarfs, as I mentioned earlier, they're low-mass stars. Their mass is about 0.1, 1/10 to 0.5, a half of the mass of our sun. And we came away, one of the most robust studies came away, just to sort of nail down a single number rather than a range, of 2.5 planets per M-dwarf and 0.24 habitable zone planets per M dwarf. So 1 in every 4 M dwarfs should have a habitable zone planet. And given that M dwarfs are the largest population of stars in our galaxy, basically M dwarfs are the low mass end, there are more low mass objects than there are high mass objects in the galaxy. So we have very few very high mass stars, and the lower mass you go, the more of those objects there are. And M dwarfs are sort of the lowest mass of the stars, and therefore the most populous. There are many, many M dwarfs just in our local neighbourhood. And we're now saying that there are 0.24 habitable zone planets per M dwarf. So we're saying that there's quite a few habitable zone planets out there. And another thing we came away with is stars are typically more noisy than our sun. That was an interesting thing that we came away with, and I'll talk about that in a moment, because it feeds into the difficulty, the challenges we have with trying to find M dwarf exoplanets using the Doppler velocity technique. And Kepler stars, unfortunately, we found all of those wonderful stars. The Kepler, I forgot to mention at the start, the Kepler Space Telescope was staring at a small area of the sky, about the size of the moon, okay? And it stared at it for 4 years, and there aren't a lot of bright stars there. They're stars that we have a magnitude system, a logarithmic system. The stars there are about, well, let's see, 100, about 1,000, a few thousand times fainter than the eye can see. And what we really want, that is in magnitude ranges about 12th magnitude down to about 16th magnitude. What we really want is bright stars. We want bright stars because when we've got bright stars, we can start to try and look at the atmospheres of the exoplanets that we find. So Kepler stars, although we've found so many exoplanets, they're extremely difficult to find out anything about those exoplanets other than that they're there. And that's a real disappointment. It's great to know that there are so many, but we don't know much about them. There are a few stars that were bright enough that we've done detailed studies and we now know a bit about them, but they're not nearly bright enough for that atmospheric study that we really want to push the knowledge of what life is like, what the environment is like on these exoplanets. So now I wanted to briefly outline what Kepler data really looks like and then what we can get out of it. So when we get Kepler data, it's a space telescope, it's pointing at one area of the sky. We look at one particular little region of the camera and measure the brightness, the total amount of flux we measured from a star in that area. And that looks like this top line. This is a pretty bad sort of a cutout of a paper, but I couldn't get a hold of the raw data because they tend to process it themselves to try and find the exoplanets. But this is what it looks like. What you've got is this variability, and this is a long period of time here along in terms of days. You've got this variability, and then you've got these big steps, and that's as the Kepler Space Telescope is orbiting around the sun. It's in a trailing orbit behind Earth in the same sort of orbit as Earth is in, but not orbiting around Earth. As it's trailing around, every now and then it has to rotate to point at the same area of sky. And when it rotates, it's now getting a different amount of background contamination from the sun. And so you get these offsets. But when you take away those offsets, then you get something that is incredibly stable. It might look quite variable, but we're talking about a variability with an amplitude of about 0.5%. So a very, very small variability, but this variability is due to things I'll talk about in a moment, magnetic effects, rotation, and things like that. This period you can see here is very likely the rotation period of the star. And then we try and smooth through all of those effects, and we get this nice, extremely stable light curve. And when we take something like that, we look at many, many stars. Some of them look a bit like this. The top line of this is the Kepler object of interest 854, is it 5? Yes, 854. You've got this data, and every now and then, marked by the red dots, you get this dip in the light curve that you can't see very clearly here. But if you were to fold the light curve at that period that you detect the dips at, and then zoom in just on the region of that folded light curve that has the dips, then this is what you see. Okay, a small dip. You can see the error bars are quite large, but a small dip in the light curve, that's corresponding to that blocking out of light. So it's not quite as clean as in the graphic I showed you before, the ideal measurement of a transiting planet, but this is the reality that we face, and this is finding a planet that has a depth. You can see the relative depth here is about 0.01% of the radius of the star. The radius of the planet is about 0.01% of the radius of the star. So depending on the radius of the star, then you can work out what the radius of the planet is. Oh, yes, these are from various papers. So, now, I've got there, what is this noise? The noise I'm talking about, the stellar activity that I mentioned that I wanted to discuss with regard to Kepler and also how it feeds into my ability to discover planets using the Doppler velocity method, is this here, this residual variability you have on short timescales just due to the star's intrinsic variability. This is a real limitation in terms of being able to detect transiting exoplanets. And like I said, what we found is that we expected other stars would be mostly like the Sun. It turns out the Sun's a little bit quieter than other stars. On average, other stars are about twice as variable as the Sun. Keep that in mind when I show you the next slide, which includes, if it's going to play, no, it's not going to play, I have to find a way of making it play, a little video from the Solar Observatory. So this is showing you how quiet the Sun is. It's the Solar Observatory it's showing particular effects of the Sun. So you can see it's not a perfectly uniform sphere illuminated evenly and giving out perfectly even amounts of light, although this particular video is focused on interesting things like prominences and magnetic effects. But this is real time, I believe so. Yeah, these are videos from the Solar Observatory. There's the transit of Mercury, that one. And that's in a different filter, the H-band filter. It's stronger, it's showing magnetic effects. Actually, I've had that in there from a different point of view to show that magnetic effects tend to be stronger in the centre of the rotating frame of the Sun. But anyway, this is showing you that the Sun is not perfectly stable, but the Sun is actually a bit quieter than most other stars. That's what we found out, and that means that we get this jitter that makes it quite difficult to be able to detect transiting planets, and also the same sort of magnetic activity, which is we call it activity. It's due to magnetic effects like these, which are occurring because essentially at some parts of the star, and particularly in certain types of star, you have a more efficient way of transmitting the heat from the core, which has got the nuclear fusion, out to the outer side, is convection, just like you get in a boiling pot, rather than radiation. So what that radiation is, where you've got producing high energy photons that are being ejected from the core and travelling through the surface of through to the surface of the star by being absorbed and re-emitted. Instead of that, you can actually have moving large pockets of gas. And so you get this surface that's sort of roiling and bubbling. And when you see that, those are charged particles, because it's so hot that it's thrown off the first few electrons of the atom, the outer electrons, and it's actually charged. So when you have charged material moving around relative to each other, you build up knotted magnetic fields. It creates these magnetic field effects, and all of that plays into the variability in the surface of the star, and also into the Doppler velocities, which I'll talk about in a little bit. So low mass stars, I particularly want to focus on those. I want to try and shift away from the general stuff to the low mass stars, because are they really good? There's a problem with them that I haven't discussed yet. Kepler said they're good targets because there are lots and lots of planets around them, lots of potential for those planets to be potentially habitable planets. What about things like Earth, like exoplanets? Now I wanted to talk numbers. Well, I talked about how we can measure the precision of our measurements for the speed of a star towards or away from us are down to about 1 metre per second. There's some efforts to try and pull that down to a tenth of that, 0.1 metres per second, sort of a fast spider or something speed. But would that actually enable us to be able to detect something like an Earth-like exoplanet? Well, Earth has an influence on our host sun. That is, the sun is moving around the Earth-Sun centre of mass with a speed of about 10 centimetres per second. So you think, well, if we can get down to 10 centimetres per second, then we might be able to measure it. But the variability in the Doppler velocity we measure from the sun is about 1 metre per second because of all that activity I talked about. So the best precision, even though we can measure, like I said, the precision down to 1 metre per second, there's an additional noise on top of that that's saying, even though you're measuring my motion to 1 meter per second based on the amount of light you got from me and all of the spectral lines, which I'll talk about in a minute, I'm actually varying my surface so much that you can't get a better precision than 1 meter per second. So trying to detect Earth with a 10 centimeter per second amplitude in terms of those radial velocity curves we were looking at before is actually going to be incredibly difficult, nigh on impossible, unless we find some special way of trying to counter all the effects of that magnetic activity on the surface. Whereas something like Jupiter mass planets around Sun-like stars we have been detecting for the last 15, 20 years, has an amplitude, induces an amplitude in our Sun, a motion around the centre of mass, of about 10.5 meters per second. That is something we can definitely measure. If we take an Earth-like planet and put it in a potentially habitable zone orbit around an M-dwarf, that is with a mass of, say, 0.3 or something times the mass of our Sun, the habitable zone period of orbit isn't 365 days like it is for Earth. It's now only about 50 days. And the amplitude of the motion of the star due to the orbit of that exoplanet is now about 1 to 1.5 meters per second in amplitude. So we can actually detect that with our radial velocity precision. So that's what I'm trying to talk about here. Oh, I've pressed the wrong button. Here, hotter stars, Sun-like stars, cooler stars. What's happening when we go from hotter stars to cooler stars is the habitable zone is coming in. And this is because hotter stars are usually the larger mass stars. They have more pressure in their core. They have more fusion going on. That fusion is emitting more light. The surface is more hot, emitting more light, and therefore the stars have to be further away to receive the same amount of light as around a smaller star. Now, the habitable zone obviously around a Sun-like star is around about Earth, but it actually stretches out a bit further. We call Venus sort of a good boundary of the inner habitable zone. Of course, Venus isn't actually habitable, and that's to do with chemical atmospheric effects. But its position relative to the Sun and its size would say that it could potentially be habitable. But we can actually extend out to about 1.5 times the distance of the Earth to the Sun before we reach a temperature that is too cold to be potentially habitable, depending on the atmospheric makeup. In that case, the atmosphere would have to be a little more carbon dioxide, a little more greenhouse to keep the heat in. But based on those sort of simple approximations, we can work out what ranges around different stars are considered habitable. And around cooler stars, M-dwarf stars, it gets right in there. Around the coolest of M-dwarf stars, the potential habitable zone goes into only 9 days, an orbit of just 9 days. But around the hotter M-dwarf stars, it can stretch out to 70 days or so. And so we can actually really detect those exoplanets that are potentially habitable around cooler stars, whereas we just can't do that around Sun-like stars. It's just not possible. So this is why we have to look to the M-dwarfs as our future for trying to find potentially habitable planets and for trying to find life. But there is an additional difficulty I haven't talked about. I don't know whether I've actually got it in the slides here. That is another thing that I haven't mentioned. I didn't really know whether I'd have time to, but I'll just throw it out there. We have this thing called tidal locking. That is, when a planet gets really close into a star, they interact. It's exactly the same way the moon has interacted with the tides of Earth and caused the moon to, over time, only have a single face facing the Earth. The same thing happens with a close-in planet. When you get into these short period orbits that we have around M-dwarf stars, for potentially habitable planets, in only just a few 100 million years, which is not particularly long in terms of the lifetime of the planet, it should be able to synchronize such that it only has one face constantly facing the star. And there are some pretty good reasons to think that that would make habitability quite difficult. But some recent modelling is saying not necessarily impossible. So just because we might not be looking for life on a planet that looks exactly like Earth, it could look still, it could be potentially habitable. In a situation where you have one face facing the star, one face of a planet constantly facing a star, you obviously have one very hot side, and you would think you have one very cold side. There's a lot of argument to say that the atmosphere in that situation would be either blasted out on the hot side or frozen out on the cold side. But there's some good atmospheric modelling work showing that with the right kind of atmosphere and all with a substantial amount of water on the surface, you can shift enough heat that you actually get a moderately warm, cool side and a really, really hot, hot side. And so you have a very wet, rainy, moderately warm, cold side of the planet where essentially the water is shifting the heat round to the cold side of the planet. So I wanted to mention that brief. I assume that I'm still going okay for time. Okay, pretty much wrapping it up. So that I pretty much want to talk about. I think I've talked mostly about what we've got there, that it's easy to detect around these low mass planets. They've got a close habitable zone and RV amplitudes, for example, for a 5 times the mass of Earth planet is 10 to 1.5 metres per second going in the reverse direction as we go from lower mass host stars up to higher mass host stars. So they are the best chances we have for rocky, potentially habitable zone planet detection in the near future. There was another thing I wanted to talk about. I'm going to sort of skip through it a little bit here. I use the Anglo-Australian telescope. In fact, I only just got off there, not last night, the night before. But I wasn't doing this particular program. Looking at M dwarfs. M dwarfs also have a particularly excellent spectrum. This is a description of the instrument I use. We point multiple fibres on the sky, getting a spectrum of the M dwarf. There's a spectrograph. It's not actually the one I use, it's a different one, but it would give a similar sort of a result. And here's the kind of spectrum I get. I get these sort of lines across here are the actual spectrum of the M dwarf. We have these bright sort of dots, which are a calibration fibre I need so that I know the wavelengths of the light that I'm looking at. Then we have all the typical sort of difficulties. So we get this in different bands. We've got a band here, another band here, another band here. And we get all the difficulties you get with real data. This is a blodge that shouldn't be there. It's reflected light. This is a bad part of the camera. In reality, we have cosmic rays and things. Real data looks pretty ugly. We do a lot of cleaning before it usually gets shown to people. But from that, we can actually extract the spectrum of an M dwarf star. And when we do that, when you look at all the variability and as we move across in wavelength in the image, you sum all that up, you get a spectrum that looks like this. We've got a hot star spectrum up there just for comparison. That's maybe a little extreme. A sun-like star would have less lines, but it would still have some absorption features. What this is telling you is that in the outer layers of the star, there's lots and lots of different absorptions of light. So coming from the core fusion, we have this continuous spectrum of light, just like coming out of not those kind of lights. Normal tungsten bulbs, a continuous spectrum of light, but then in the outer layers of the star, depending on how cool they are, different molecules absorb. And M dwarf stars are special. They're so cool, they actually have molecules rather than atoms absorbing the light. And when you have molecules, you get an additional little benefit. Molecules don't just absorb light through electron transitions like atoms, which are just some sort of nucleus with electrons to absorb, but molecules are bound to atoms together. In this case, they're actually ions. They've lost a few of their electrons, but they're bound together, and now you can store energy in a variety of other ways, vibrational states and rotational states. And as soon as you do that, you get these huge number of transitions that cause all sorts of different absorption lines at different wavelengths, different colours. Whereas in a hot star, you don't get that. What that means is that essentially, if I was to move this spectrum a tiny, tiny little bit to the left or a tiny, tiny little bit to the right, you would notice the difference. But if I did that for that one up there, you wouldn't be able to tell. Essentially, what enables us to be able to tell whether a star is moving towards or away from us, blue shifted or red shifted, is essentially the amount of absorption features we have in the spectrum. And M dwarfs are really, really good for that. So I know I've gone on a little longer than I'd like, but if I can briefly talk about the actual discoveries, and Shane mentioned I was going to talk about it. This is the kind of radial velocity time series we get from looking at M dwarfs over time. This is a few years worth of data. We ramped up the number of observations that was observed towards the end, and the variability we're seeing in its velocity is only just a few metres per second, about 16 metres per second from top to bottom. This was HARP spectra. It wasn't actually taken with the AAT. It's the High Accuracy Radial Velocity Planet Search Spectrograph in Chile. And when we try and find planets, we take that data, that time series of radial velocities, and we try and fit sine curves, these standard curves, to all this different data phased at different periods. So we fold it at particular periods and see what amplitude of sine curve fits that data. And when we do that, we find peaks where there is a good fit to the data. And what we found around this particular star, which was Wolf 1061, I actually chose the name Wolf 1061 as opposed to GL628 because it had the word wolf in it, and I thought that was kind of slightly more exciting than the standard HD numbers and GL numbers we have for these stars. That was about the only thing you get to choose when you actually discover a planets around the star, unfortunately. But what I'm trying to show here is that we had these really clear peaks in our periodogram. That is where we thought planets were actually occurring. And then these lines show us the probabilities where the probability of having a random occurrence event is 5%, 0.5%, and 0.005%. So these peaks are extremely unlikely. And if we fold the data, that radial velocity time series in the background at that particular period, which is the planet, the main planet that got attention for Wolf 1061 because it was in the potential habitable zone, this is the kind of real folded data that you get. So you can see a clear periodicity, but there's still a lot of noise there. We can only just discover these potentially habitable planets. And only in a star where things are pretty quiet, there's not a lot of other peaks. If we look at the recent discovery, Proxima Centauri, and see how hard they had to work to find that planet, here's the data 1 year ago, not including the data they got in this last year, because I didn't actually have access to that. Oh, I went the wrong way. Here's the periodogram of that data. Like I said, I don't have the latest work, but what you can see here is the periodogram does not have a single clear peak that indicates the planet, kind of like the periodogram we had a couple of pages ago. Up the top, I had several periodograms, but that one on the top left was the primary planet. This peak you see here is the one that was determined to be the planet around Proxima Centauri at 11 days. Not these. This is activity. This is the roiling that happens. And Proxima Centauri is one of those particularly active stars. And they took a lot of data over 1 year since that period to try and understand all of this activity and be able to remove it to be able to find that planet. I still have my suspicions that handling that much activity is extremely difficult. But that's the kind of process we need to be able to deal with to find more of these potentially habitable planets. So can we examine the atmosphere of those kind of planets? No, we can't. Unless the planets are transiting, it's not possible with current or planned instruments to be actually able to detect the atmosphere of these planets. What we need is a way to discover many Earth-sized transiting exoplanets orbiting bright stars, and that's the future. I will very briefly, because I know I'm running over time, just show you a couple of videos, a couple of slides describing the Transiting Exoplanet Survey satellite that's coming online at the end of next year, which will discover tens of nearby bright M dwarf, potentially habitable planets. It's going to provide us what we need so that we can study into the future and find and study the atmospheres of begin to study the atmospheres of exoplanets, something that we're only just trying to do at the moment. And the James Webb Space Telescope will be the telescope that enables us to do that. You've possibly heard of both of these. Definitely the James Webb Space Telescope you should have heard of. It's kind of like a Hubble replacement. It's not. The real Hubble replacement is planned for 2028. The JWST is going to be coming online, well, definitely by 2020, hopefully 2019. And it's going to have the kind of instrumentation needed to be able to examine the atmospheres of transiting exoplanets, although it will struggle with Earth-sized exoplanets. It'll probably be pretty good for the sort of Neptune-sized planets. I won't dwell on this. TESS's got a 2-year mission. It's going to start in the southern hemisphere. It's observing 200,000 stars across the sky. Most of those are going to be M dwarfs. And it's going to be doing exactly what Kepler did, looking at very, very precise photometry to try and find the transits around nearby bright stars. Stars that are bright enough that we can actually follow them up and try and investigate the atmospheres of the planets. The same problem they're going to have is what Kepler has, that is that transit noise, the noise that occurs due to the star's variability. And the total time on a star, the total time series they'll have will be limited depending on the different position of the sky. The stars above the pole will get a full 1 year looking at them from tests. And then we have the James Webb Space Telescope, which has a nice little video showing what it's going to be trying to do. It's essentially got a low-resolution spectrograph that breaks the light up from the star into its various colours. And so as the planet transits across the star, and we're going to see a little part of that video there, a small amount, you can sort of see the fuzziness around the outside, a very small amount of the light of the star goes through the atmosphere of the planet. And so that starlight gets imprinted with the atmosphere of the planet. We're talking about an incredibly small percentage of that spectrum imprinted with the light of with the atmospheric makeup of the exoplanet. But if we subtract the spectrum of the star when the transit is not, if we subtract the spectrum of the star when the planet is not transiting from the spectrum of the star when the planet is transiting, then essentially what's left is that spectrum from the exoplanet. So that's the incredible difficult challenge that we're just trying to take on now. And through doing that, we hope that we'll be able to discover more about the environment on these exoplanets. And here's just a few predictions. That is, TESS is definitely going to give us many potentially life-containing planets. Being able to study those is going to be challenging. JWST may be able to find signs of life on some of them, and that's going to be in the next 5 to 10 years. In the future, follow-up telescopes already being planned for 2040, 2045, probably by the time it actually gets up and running, are designed, and I think we'll likely be able to find the signs of life in the atmosphere of several of those transiting planets that we will find in just the next few years. So I think that's all I've got. I apologise for going over time, but thank you very much for listening. And, I'll definitely take questions. Yes.
Duncan.